Hello, everyone. Welcome to today's Tech Talk. This is on troubleshooting Kubernetes the easy way with generative AI and ML for automated RCA. And as we all know, RCA stands for root cause analysis. I'm Patrick Hubbard, part of the technical product team here at ScienceLogic. And joining me is Gavin Cohen, Vice President of AI Product Management. How are you doing, Gavin?
Very well. Looking forward to presenting here, Patrick.
This is really exciting. I actually came to Lens sort of the way that a lot of people from sort of enterprise IT do, right? Which is I suddenly found myself managing a couple of Kubernetes deployments and was looking for something to make that a whole lot easier. And it's great to be able to speak to the audience and the team and everyone else who is working with these products. So let's go ahead and get started. And we could just do a brief overview of what automated root cause analysis is, the problems it solves, and then we're going to do a live demo, and we'll actually be able to see that in motion. All right. So the first thing, I think the thing that we always see as a challenge is what do we do when an application breaks? But with Kubernetes applications, it can actually be a little bit harder to troubleshoot, especially in this case, the application that we're going to look at here in the demo in a second, where there are over 40 different microservices that actually pull that all together. And the challenge, of course, is that the spinning delay wheel in the user interface is not helpful for anyone. And figuring out where to start troubleshooting, or even be able to have the assets that are necessary to be able to troubleshoot, can be really challenging. I mean, someone has to figure out that root cause, right? And especially when you were looking at log analysis as a part of troubleshooting, especially for novel issues that you haven't seen before, one of the big problems is you don't really know how much time that's going to take. For fairly well understood issues, it may be pretty quick. You may know what log to go to. You may have the credentials that are necessary to access it. And you may even have an understanding of the application itself and where it tends to break. But a lot of times, the ones that can cause really serious outage, it is a series of troubleshooting steps that just build one on top of the other. And to finally get to the root cause, it can sometimes take a long time, and especially be a little bit nerve-wracking if you've got people pacing back and forth behind your chair asking why you're still down, because you don't necessarily know when the end state is going to be. You don't always know how long it's going to take to troubleshoot. And logs, of course, are really, the best place to find root cause. I mean, metrics are fantastic, right? They tell us something happened. They can identify exactly when it happened, and they can cohort a lot of times a bunch of different metrics to show sort of the overall blast radius of that outage. So it's really, really helpful. And traces are really helpful because they can tell us, really where it happened in application flow, right? We can actually see that somewhere along that process between an actual human user who's connecting to those systems and the backend services which are providing it, you can actually see where that break is. But neither of those tell us the why, right? They are not specifically going to be able to point at a single issue that's actually caused that cascade of issues that resulted in the failure. And they're really sort of, I think everyone on this call knows how indispensable they are, except most of the time we don't really do anything with them, right? They're sort of the digital exhaust of applications and infrastructure, and we don't always have a whole lot or even budget necessarily a lot to be able to pack them all away where we can do something with that. They're also really noisy, right? And in a lot of cases, they're unstructured, and they're as individual as the teams of application developers who actually have added, the log messages and the logging events that are actually, being persisted. And there are a lot of them. And especially with Kubernetes, they are intentionally ephemeral. And if you're lucky, right, you have some sort of a mechanism to concatenate those and pull those all together. But that is still a tool that in most cases are largely driven based on query. And again, an understanding of the data and the individual sort of messages to be able to drill down under pressure and be able to identify what that cause of the problem is. So logs are immensely valuable, but they are really difficult and challenging to pull together into a mass of evidence that is easy to then process and identify root cause. And, I mentioned it before, it can take hours in some cases, right? Especially when you consider how many logs there could be in a Kubernetes deployment, especially large ones with a lot of horizontal scalability. There could be dozens, hundreds, or even thousands of different log files, especially where you have lots of services starting and stopping. They may or may not be persisted. And the relative rarity of some of the logs, some of the issues that can cause real outages is pretty high, especially for applications, and especially for applications that you're working on really quickly. They can be as unique as the developer that actually creates the log message. in sort of old school packaged applications or network logs, for example, they're pretty well structured. There's been some time that's gone into it. But today, the relative rate of change doesn't let us do that. And so those understanding, like the necessity of having a skilled human being to actually look at those logs and understand what they mean can be pretty high. And that means that we use a lot of intuition and a lot of experience. There's a lot of cognitive bias. There's a lot of other things that happen as a part of that process of going through logs and actually grepping out and trying to find what the issues are. And so, of course, we just continue to iterate over and over and over again, and then hopefully, eventually, find a needle in the haystack. So in this case, we're going to show you something a little bit different. And in this case, we're talking about a technology that's a part of the Skylar Automated RCS solution from ScienceLogic. And in this case, we're going to demonstrate how it's actually using machine learning and artificial intelligence to actually automate that process of troubleshooting issues from log files. Now, I don't want to oversimplify this, right? That basically logs go in and root cause comes out, but it effectively looks an awful lot like that when you work with it. And I know that's an enormous claim. We're going to do the demo in a second, and we'll get into how the technology is actually able to deliver this. But the goal is for your team to be able to identify issues, to not waste time going through dozens, hundreds, or thousands of log files, trying to find issues when you are actually down in production. That is the goal. And that is what this technology is designed to do, is to take away the labor and the difficulty of the steps of getting logs and getting the information in logs available so that you can identify root cause. Rather than continuing to talk and hit slides at you, I mean, certainly as an engineer, I don't like them all that much. We're going to turn it over to Gavin, and he's going to walk us through a live demonstration of how this actually works.
Hey, thanks, Patrick. And just let me set up the demonstration, because hopefully this will make a lot of sense to you guys and girls out there. Essentially, what we've done is we're using the Hotel Demo app. It's actually a pretty cool app. It's an online shopping app. It has, I think, 42 services. So lots of pods and containers and things happening. And it's all, uses a whole bunch of open source components. But it's a nice kind of demo app because it's busy, it's big, it's got lots of complicated interactions between services. And so essentially what we do, just as a great way to showcase this kind of machine learning technology, is we set up the demo just simply by using Helm to deploy it, nothing special. And then we were trying to find some sort of cool ways to break it. Obviously, there's some easy ways like, whatever, scaling pods down or other things like that. But we wanted to find kind of a more subtle way to break it. And so what we did, we sort of experimented a bit, but we found kind of an interesting sort of breaking scenario where if you look at all the services, right down the bottom, there's the feature flag service, which is it's not in the primary data path. It's just that some of the other services query it now and then to figure out what features to enable. So, in a sense, it's kind of a little bit removed from the whole process of what the online shopping app does. But
Gavin, are you suggesting that a seemingly unrelated aspect of an application can actually bring it down, and that would be hard to identify the issue?
What a surprise, Patrick. Go figure. But anyway, so the way that we tried to break it is underneath the feature flag service, it stores its current state in a little Postgres database. So it's a tiny little database. And what I did is I logged into the Postgres pod and just changed the password for the feature flag service user. And it was pretty cool because soon after doing that, the UI froze. This is the slide that you saw earlier. And now you're kind of left in this world of how do you figure out what happened? Now, obviously, I know what happened because I broke it. But if you came into this cold and you said, okay, I've got all the tools in the world available and Prometheus and Grafana and all kinds of things watching and I've got Lens to go and click on, look in logs. How do I really figure out what caused this in the quickest possible way? And it's actually pretty subtle because the breadcrumbs that explain it they're hidden in one of the many logs. And in fact, if this were a live app, you probably wouldn't first go to the feature flag service to figure out what went wrong. You'd probably start somewhere else. But net is we set this up, we broke it, The only thing we did is we installed an OTel collector to stream the logs to the Skylar Automated RCA instance running, so that there was no pre-training, there was no pre-knowledge of this app or this environment or what is good or what is bad. It all uses unsupervised machine learning. But essentially, we just installed the OTel collectors. They were streaming all the logs from all the different containers across to the software. And then we broke it, and we kind of pretty interesting what popped out the other end. So what I'm going to do now is I'm going to flip away from the slides that everyone's probably sick of at this point, and I'm going to jump into the user interface of Skylar Automated RCA. And what you see here is called a suggestion, okay? And I'm actually going to make the font a little bit bigger, just so it's easier to read. But essentially, a suggestion is what the machine learning picks out of all the logs that it's looking at. And when I say logs, the log lines, when it thinks there's a problem. So essentially, it's a collection of log lines that the machine learning thinks represents a problem, and it's presenting it in kind of an interesting way. So what I'll do to explain it is I'll click on it and I'll drill into the suggestion. Okay, and let me sort of walk you through what you're seeing here. So first of all, remembering it's unsupervised machine learning used to generate this. There were no rules in place. There was no prior understanding of this environment. Essentially, we spun up the app. We let it run for a couple of hours, literally, so it could learn the normal patterns in the logs. And then we went in and changed that password of the feature flag service user in Postgres. So what you see here is, if I start on the right-hand side, there's this number here, 37 events that you see here, is the machine learning picked out 37 discrete log lines that it thought represented a problem, okay? And this is, think about it as 37 out of millions of log lines that were flying by at the time coming in from the OTel collectors, okay? And you can actually see on the bottom here, there are all these little histograms of log lines, but this represents the spread. There are 37 of these, dots that you see over here, and the histograms and the names of the logs that they came from, or the pods that they came from, are represented in these little charts on the right. But really, the interesting thing and the core of the machine learning is what you see here, and these are the exact 37 log lines. And remember, they're not consecutive log lines from one log stream. They're an interleaved set of log lines from all different places that the machine learning's picked out. And even within a single log stream, like you see here, the third column represents the name of the log stream. It's actually the pod name. So the third stream here, you see there are a couple of log lines from the front end. Here's one from feature flag service. And then here's one from Postgres, and then you can see, and so on. So there's a whole collection of log lines. But if you walk through this third log line here that says fatal password authentication failed for user FFS, this is actually the root cause, right? This is as close as you'll get to what broke the app. This started occurring when I changed the password. But what you're seeing here, because this is this collection of 37 log lines picked out, is you're seeing the root cause log lines, but you're also seeing the symptoms. So it starts with, there's some front end errors. There's the feature flag service. This is the root cause log line where my mouse is over here. And then if you scroll down, you see some more front end issues. Then you see a couple of Kubernetes events where it's, seeing the pod, the feature flag service pods failing. And then you go a little bit further down and you see now it's starting to hit the recommendation service. So that fails again. It's also got these dependencies, presumably on the feature flag service. And then further down, the COTS service, the ad service. So these are all kind of the things that ended up breaking that were picked out by the machine learning. Now, it's not picking them out because they're errors. In fact, this line here is just a debug log line, and some of them are warnings and so on. In fact, if you were actually looking at just errors, you would have seen thousands and thousands of them from all across the different modules. It's picking out the log lines because they're this cluster of correlated anomalies that it thinks represents a problem. And so you can see even within like this stream, if I look at FFS Postgres, where it's only picked out 2 lines here in the report, I do have the ability to do what's called peek. It lets me go into that log stream and see what else was going on within the log stream. So that's the first thing I want to point out is the core of the machine learning is picking out what it thinks are representative lines when it thinks a problem occurred. I didn't even tell it a problem occurred. It picked this out because it was watching all the logs. Okay, so that's what these 37 log lines are. If I go up here, now I'll explain a little bit more. Once we generate those 37 log lines, we then use a language model to try and translate them into plain language. And this is where you see a pretty spectacular result, right? This almost in one line kind of explains the problem. So it says authentication failures causing availability issues with feature flag service and recommendation service. So that's like a one-line summary with the root cause being, authentication failures. We also generate like a small, I think it's like a 500 character summary. And this gets into a little bit more depth, but also in plain English. And it's pretty insightful, actually, if you just read a sentence like this. Authentication and connectivity issues may be causing feature flag service to have connectivity issues and dependent services to fail, front-end service also, etc. The demo piece. Let me come back and I'll just use a few slides to try and explain a little bit how it works, because it sounds a little bit like magic. We're feeding in logs and then we're spitting out a root cause. So how does it work? And really, it starts with, essentially it's just an endpoint to receive log streams, and you can upload static log files using a CLI, but really the normal way is you would install an open source collector like OpenTelemetry collector or something like a FluentD, or we could take a feed from something like Logstash and so on, or we have a syslog receiver as well. So there are various ways that we can get logs in, but that's not our IP. That's all kind of common, well-solved problems. So the way it works is it starts by streaming in logs, and we don't want anything done to those logs before you stream them in. So they're all in native format. That means if they're completely messy and verbose and unstructured, that's fine. If they're structured, that's fine too. We're not assuming anything, because everything the machine learning learns from, it just learns from the logs it sees. So the first thing it does, and it sounds trivial, but this is actually the foundational piece of technology that we've built here, is it uses an unsupervised machine learning pipeline to essentially autonomously learn how to structure and categorize each unique type of log event. What does that mean? I said there were 42 microservices, so we're getting, I think more than 42 streams of logs, each emitting, whatever it is, thousands of logs a second. And within each of those streams, it's got its own event space. So there are lots of different event types and all the different severities and everything. So essentially what it's doing is for each unique event type, based on what it's seeing, it's trying to learn its exact structure, and it's using that to categorize it. And it does a really good job. This is actually the absolute foundational piece, as I said, of technology that was built here. So first it learns to categorize everything. That means you didn't have to do anything to the log lines before. Okay, and it knows as well when it categorizes them which log types those log events belong to, and it can use that to sort of inform the next stages. So once it's done that, and that's actually continuous, but it happens quickly. And the example here is we only had a couple of hours of log lines to go on, and yet that was still enough to know how to categorize well enough to have picked out the problem. Okay, the next thing it does is for each event type, it learns about that event type. So it learns its frequency and its periodicity and so on based on the log streams where that event type exists. And once it does that, and this is all happening simultaneously, really what its goal is to pick out log anomalies. But typically log anomalies are not what we do. When people think of log anomalies, they typically look at log messages that have very high frequencies, those kinds of things, because they're often indicative of a class of problems. They actually work well for some sort of web apps, but they don't tend to work well for many other apps. But what we're doing is not that at all. Because we do a good job of categorizing them, when we do our anomaly detection, we're really looking, there are lots of factors that give it, and we actually score every log line as to how anomalous it is. But the two biggest factors that impact the score are what we call rareness and badness. Because it turns out that when you're troubleshooting through logs, and we learned this by studying thousands of real life problems that showed themselves in logs, really what you're finding is a combination of rare and high severity messages. And why that? Well, errors are fairly self-explanatory. They tend to be symptoms of problems. Rare things tend to be the needle in the haystack. The log line that doesn't usually occur is usually the one that's most diagnostic in nature. And then what we do, so we pick out these anomalies based on their rareness and badness, and we do it pretty well because we've categorized everything well. But that's not good enough, because if you just looked at log anomalies, you wouldn't have distilled it down to 37 log lines. You might have distilled it down to a few thousand log lines, which is too much to pass over to a human to look at. So the next pass is to look for abnormal clusters of anomalies. And this is really how you get we pull out a signal, and then we get a finer grained signal from the noisy signal by looking for correlations. So what happens now is we know essentially the distance between any two anomalies across any two log streams based on normal patterns, and we look for where that's abnormal, and then we look for where it's abnormal across multiple different things going on. So once we do that, we tend to do then a really good job of now filtering it down to just a few log lines. And because of how the anomalies are generated, they typically represent something that is very likely to be a problem. And that's what really you saw. That was how the 37 log lines were generated. Then we do the summarization. So we created the word cloud that you saw. We pass it through to a language model to get the title and the details and the summary that you saw, the plain language one. And then that's packaged up into what's called a suggestion, which you saw you can then interact with and drill down on and so on. So that's really the whole process. So it's really about foundationally getting to the point where things can be categorized well enough, learning the patterns, picking out the anomalies, correlating the anomalies to get this, the most likely things to represent a problem, and then summarizing and presenting them. So that's really the bulk of the content that we wanted to share with you. Let me just pass it back to Patrick, maybe talk a little bit about the use cases and kind of the problems it's designed to solve. So Patrick.
Sure, thank you. And it's interesting when you're going over the how does it actually work, that set of steps that are part of that processing pipeline. It's a reminder. I think we've all sort of been under the influence of big AI at this point. This idea that artificial intelligence or GPT is a panacea, that you just throw data at it and magical things happen. And the reality is that the understanding of what to do, like in this case with working with logs, tends to be really domain specific. And a lot of the work that actually makes that technology really effective comes from really understanding the way that operations works, the challenges, and the individual artifacts and types of systems that the technology is working with. So let's actually talk about just maybe the last two big use cases here, right? The first one is sort of that well-known issue, right? When you find the root cause, when you know that there's a problem, you're clear that there is. Let's say your monitoring is, you've got a bunch of metrics that indicate that everything is running fine, and they fall off to 0, or your error counts suddenly starts to spike, and you know for certain that something is wrong. And in that case, you will start to see that problems have been detected about the same time that dashboards are beginning to indicate that there's an issue. You definitely get RCA suggestions around the same time, and they can really help identify and confirm that that's the issue. It's also a really great opportunity where you can do automation, to do automatic resolution of issues that you either expect or have seen in the past. as Gavin demonstrated before, the ability to really click the accept button and create a fingerprint so that you know that when a problem has happened, if it's occurring again, even if it's fairly novel, to be able to take action on that really quickly. So that first case of known problems or things that you have maybe done troubleshooting before, to be able to use the suggestions that are coming for a root cause to be able to confirm them and then quickly take action. Now, the second use case is the one that I think probably keeps us up at night, the most, which is to be able to catch the unknown unknowns, right? The issues that there are no rules for, that are not clearly deterministic, that there is no one, string that you could use regex to identify in a particular log message, but to be able to intuit the real cause of an issue when it's something that's never been seen before, or there's a lot of dynamic motion and configuration in an application, for example, where continuous relearning of what those log messages are, or being able to reassociate and cluster them in a way that identifies issues, right? And so in that case, Automated RCA is creating those suggestions, again, whenever it finds patterns, right? And so in this case, it thinks that there's an issue and it's bringing those to you. It's almost like, you've got maybe that one person on your team who's who's really sharp, got really great sense. Maybe they're new though, and they don't have a lot of experience with application or infrastructure or something else. And they sort of tap you on the shoulder and say, hey, I saw something here that's really strange, and then can provide the evidence to you to be able to quickly articulate what that is so that then you can decide whether that's an issue or not, right? And in that case, you will tend to pick up issues that are missed by other tools. And I think that's one of the challenges that we all have as a part of operation, is we end up with a bunch of siloed tools, each of which is really good at identifying a part of a problem, but none of them actually span across multiple issues to be able to identify what those causes are. And again, the only way that works is that the technology cannot be based on manual rules. Again, you cannot go and configure for a issue that you've never seen before, or messages that are completely unknown, or in the example that we saw before for the feature flag issue, where it was an info message that was actually telling us that there had been a change that then had caused this cascade with this, explosion in the volume of other messages as other components of that application began to fail. So that's a rule that probably no one would have thought to have add, or maybe you thought of it, but there just wasn't time, right? That's that long tail of things that we know that we need to get to in terms of configuration or monitoring or management, but often just simply there's not time or resources to be able to do that. The one caveat to that is you can pick up a lot of things that you don't care about, right? If you're beginning to if you have issues in the lab, for example, they're a part of, like in this case, where maybe if you're doing chaos testing or something else, where you need to be able to mute those, or at least to be able to recognize that those issues appeared, that they were fingerprinted and identified as a potential issue. But that's where that reject button that we didn't get a chance to show before, but allows you to say, hey, I know what this issue is. It's not an issue, and don't bug me about this again. Go ahead and categorize it. Go ahead and show that there is an instance, so that if I needed to, let's say, go back and troubleshoot, and I just wasn't getting the sort of alerts that I expected, I can go to that timeline that we saw across the top and see there's a huge cluster of rejected advisories that are coming out, and then maybe say, hey, I'm gonna take a look at that and dive into that a little bit more. But again, there could be an awful lot of noise that comes out of those, and so being able to quickly sort that is a big part of that particular way of using this technology.
Patrick, just let me maybe add a few points here, which is the reason that we separate these two use cases is a way of thinking about how do you deal with a world of false positives. So think about the first use case. The first use case, we're not using this tool to detect the problem. We're using this tool to save you the time of having to dig through logs and troubleshoot it. So something else tells you there's a problem, you've got that set up, you've got great monitoring tools in place, or users that call up when there's a problem, so there's a problem. Now, you don't have to worry about false positives because you know the time of the problem. You just have to look at that timeline and go straight to where it's telling you there's a problem, and almost certainly this is going to pick out the right cluster of log lines and help you troubleshoot it without having to have gone searching. So it's a very easy use case. The second one is a different use case. What it's saying is the machine learning picks out patterns whenever it thinks there's a problem. Some of the ones that it thinks are problems are going to be real problems that nothing else detected, that are highly valuable, that might, and it might even pick them up very early before they become, outages. So in a sense, it's like this amazing insurance thing because it'll tell you about things that you didn't know about. But the penalty you pay is it'll also tell you about things that are either not problems or, as Patrick said, they're things you don't care about. So the way we normally explain it to people is if you want to use it proactively, don't alert on them because you don't want to be alerted every time it thinks there's a problem. Imagine waking someone up saying, we've got a suggestion and it turns out to be bogus. Instead, you look at it every morning at 10 a.m. You spend 5 minutes looking at any suggestions from the previous 24 hours. If they look interesting based on the summary, click on them and decide if they're real or not. Otherwise, just ignore them. So it's really like you spend 10 minutes reviewing a few suggestions, but every now and then it's going to save you because it'll pick out something that you didn't know about that prevents an outage. So that's probably just a different perspective on why we talk about them separately. It's the same technology that picks up both kinds of problems, but one we're a detection mechanism, one we're not. So just another way of explaining that.
All right. So the first one here is, this is a good one. So how is this deployed? Right. Where does it run and how is it configured?
Yes, it's a SaaS. We treat it just as a SaaS service. So it's a multi-tenant SaaS service. Your own data lives in its own schema. I didn't show you, and let me maybe, since I'm still sharing, essentially what happens. So when you get an account, you get an endpoint and a token. And then if you want to, let me go back here. The way that you deploy the collectors is we have this thing called integration collectors, Kubernetes. In this case, it's using the FluentD. I grab this command and I paste it in and just give it, what we call a service group name, and you can set a time zone if you want. But that's really all you need to do. And then the FluentD in this case will just start streaming the logs, or we can use OTel, as I mentioned before, to get the logs across, but it is a SaaS service.
Okay, second question here. This demo looks great for Kubernetes. I assume that it will also work in any distributed system, correct?
Yes. It's not actually, this is the funny thing, it doesn't understand logs. It knows how to learn log patterns. So it'll actually work with any logs. And I say that, in a loose sense. When I say logs, they need to look like logs. So they need to be in plain text. They typically need timestamps, and at least some of them need severities. But there's not much else that you need to care about. And we typically want lots of logs and variety of logs. One log stream is much harder, obviously, to pick out correlations and interesting patterns than multiple, where you're doing all the cross correlation. So typically, as long as there are multiple logs and they all are just kind of, a human would consider them to be logs, it should work. And it's not trained on any particular software or any particular type of problem. More, it's trained on the same process that humans use to troubleshoot. So I think Patrick went through that slide earlier and he sort of explained, what do humans do? Well, you try and find the right log streams, you look for familiar words, you look for rare log lines, and so that's really what the machine learning is doing. It's mimicking what an expert human would do if they were just given a bunch of logs and told to go and find a problem.
Next one, is this real-time analysis?
Everything's micro-batched just for efficiency, so it tends to lag by a couple of minutes. But it's essentially doing it all in real time. So you typically within a minute or two of one of these things showing up, you'll get the suggestion will pop up.
Do you have group log resources? So it's not trying to correlate data, let's say from AWS or Azure on East versus West that may have nothing to do with one another. So I guess what he's asking here is the ability to segment logs and messages so that you can get general categorization and assignment by maybe group, responsibility, or application tier.
Yep. So if you were very sharp-eyed when I showed you that, like how you would paste in the helm command to install the log collector, one of the parameters you pass in is called service group. And that's what essentially it's like a failure domain. It's the group of logs that it should correlate against. And you don't want that to be too broad, or you'll get, it's more likely you'll get, extra log lines that you don't care about showing up, or you'll get too much noise in the the suggestions. But typically you want to pick the group of logs that are associated that a human would look at when there's a problem. So if it's an app, maybe it's the app logs and the middleware logs and the OS logs, but you wouldn't necessarily want to put in every single log from every component in that environment because a lot of them are unrelated. So that's what a service group is. It also supports the idea of where you have discrete, environments, you can also have things called deployments. And so there's a bit of a hierarchy. So you have deployments, and within deployments, you have service groups. So there is a way, and it's an important piece of configuration that has to be provided if you want to use this well.
From a cost management perspective, do you store all the log messages or just the fingerprints or digested message lists?
That's a very good question. We do not store all the logs. We need to see all the logs. So you have to, every log line has to fly by. We buffer them for a short period of time, enough to get correlations, and then we throw away, when I say the vast majority, 99.999% of stuff gets thrown away because it's not diagnostic. It's just the noisy, spammy ones. The only thing that gets picked out are the ones that you saw that go into suggestion. So we do not store all the logs.
Here's one. Are there any notebooks or coding environments like Jupyter Notebook that can be integrated with log files to help us understand behavior of our in-tier applications?
I think I need to understand what's behind that a bit more. We don't integrate with that, but in general, the way our integrations are more, they're outward bound, so we can show suggestions on dashboards as one type of integration. We can also send suggestions to other tools like Teams or Slack or WebEx, Teams, those kinds of things. Or some of the incident management tools like PagerDuty or OpsGenie is predominantly the integrations we have. But it is all API driven, and you can also, it has this concept of signals. So you could send a signal when there's a problem, and then we can respond with what the machine learning sees around that time. But I'm not fully clear on what's behind that question. So if you want to maybe give more detail, that might help. So apologies if I didn't directly answer it.
Feel free to, when you ask that question, sir, please feel free to provide some additional detail. I think part of it, and maybe it's a great idea, is to actually have plugins for different development environments. Might be really cool. This last one is, how far down the stack does this work? Does it only work at the app layer, or will it continue all the way down the stack into infrastructure?
Yeah, it's really whatever logs you send is how far it goes. So in general, like I said, in an ideal world, you'd want to see at least the app and the components that make up the app, as well as the OS logs. If there are closely related other infrastructure logs, those could be fed in as well. So it's really more the variety that you want. It's not, it's not specifically designed like if you just fed it, only network logs and no other context, it's probably less likely to pick out the really interesting things because it has no visibility to find the right correlations. But it can look across really anything. It's all just depends on what logs you feed it.
And if you would like to learn more, or actually there's a free trial that's available for Automated RCA, check out the link below. I wish that this one's a little bit less hyphenated, but it is sciencelogic.com/automated root cause analysis with hyphens. And that'll take you directly to the page. Of course, you can just visit sciencelogic.com and you'll find it right there on the front page as a part of the Skylar AI feature set that's a part of the ScienceLogic technology stack.
So let me quickly introduce our upcoming webinars. So we've got 2 upcoming webinars. The first one will be the day after tomorrow about OpenStack demo. And another tech talk will be on August 13th about best cloud native languages to treat infra as code. So feel free to register.
That brings us to the end of the presentation. Gavin, thank you again so much for all of your time. I know you and I have had a lot of fun with RCA, working on demos here, and especially troubleshooting the stacks like for the demo that we saw earlier here using Lens. And it is just great to be able to have an opportunity to chat with all of you all as a part of the community.
Right. Thank you, everyone.
Awesome. Thank you, everyone.